Think of standing in a tiny patch of curved space-time, just a small region, so small that you don't have to worry about big sweeping changes in gravity. In that little neighborhood, energy is completely accounted for. Whatever flows in must flow out or remain inside, so it's not like energy magically appears or disappears. That's local conservation of energy, and general relativity, GR, fully respects it. The real puzzle comes when you try to tally the energy of an entire curved space-time, say, the whole universe or some big chunk of it, and then expect to see that total value remain constant over time. In familiar, non-expanding scenarios, such as flat space-time in special relativity, you can often do that because there's a nice uniform way to define time for the entire region. You can say, if I shift everything in time by the same amount, nothing changes. That's basically a time translation symmetry, and it's the reason energy is conserved in the simple sense we learned in basic physics. But in general relativity, spacetimes can be dynamic and curved. A classic example is our expanding universe, which is definitely not static. As the universe expands, wavelengths of photons stretch out, they get redshifted, and each photon's energy goes down. If you try to add up the total energy in light at one moment, then do the same thing a few billion years later, the numbers won't match. That doesn't necessarily mean energy is lost in the usual sense. Locally, at the level of small patches, conservation of energy isn't violated. There's no point in space where energy just vanishes. Instead, it's that the overall geometry of spacetime is changing in a way that doesn't let you define a single unchanging energy budget for the entire universe. This is tied to the deeper idea that gravity, in GR, is geometry itself. There's no separate, universally agreed upon energy contribution for the gravitational field, the way we might have for electromagnetic fields. In electromagnetism, there's a well-defined energy density for the field, so we can say, this is how much energy is stored in the field. But in GR, gravity is not something that sits on top of spacetime, it is spacetime geometry. Because of that, there isn't a single, gauge-invariant way to talk about the energy of the gravitational field in every situation. So how does all this relate to the saying energy isn't conserved in general relativity? On the surface, that statement can be misleading because local energy and momentum conservation absolutely holds. There's no breakdown of physical laws in tiny regions. What's being referenced is that you often can't attach a single number to the total energy of the entire spacetime and watch it remain fixed in every situation. Especially in something like an expanding universe, you just don't have that neat time translation symmetry. Instead, the geometry itself is dynamic and changing, which means your intuitive notion of energy budgets gets trickier. One of the most common examples that sparks confusion is cosmological redshift. Light traveling through an expanding universe loses energy as its wavelength grows, so you might ask, where did that energy go? Locally, if you zoom in and follow a photon's path, you'll see that nothing is actually being destroyed, it's more that the photon's energy gets redefined by the stretching of space. There isn't a single universal frame of reference in which we can say, there is a fixed total amount of energy at all times. That concept just doesn't exist in a straightforward way for non-stationary spacetimes. Another piece that adds to this confusion is that, in many physics classes, we're used to hearing a rule that energy can't be created or destroyed. That's absolutely correct in contexts like Newtonian mechanics or special relativity, where we have a nice, stable background. In general relativity, that rule still applies locally, but globally, the geometry can play tricks on us. It's not that energy pops into existence or winks out, rather, the measuring sticks themselves, space and time, are changing. If your measuring device for time or distance is changing in a complicated way, then your global energy measurement may not stay fixed. When space-time is nice and neat, flat at infinity or stationary, time slicing the universe in a consistent way becomes possible, and we do get a total energy that stays put. If you imagine stepping infinitely far away from a star, or staying outside a black hole in a region of space that isn't too warped, then you can treat that region a bit like standard Minkowski space, define your energy, and see it remain constant. In a dynamic or expanding situation, that luxury often disappears. So, to sum it up, locally, no issues, energy is conserved in the sense that if you take a tiny region, energy doesn't magically come or go. Globally, in some special, well-behaved spacetimes, we can define a total energy that's conserved, which includes contributions from matter, radiation, and the gravitational field. But in a vast, rapidly changing cosmos like ours, the total energy of the universe isn't a single number that remains the same forever, which is what people usually mean when they say energy isn't conserved in GR. It all depends on whether the structure of spacetime allows you to define that global total in the first place. Thanks for watching. I hope you enjoyed the video. If you would like to see more myths of physics explored, please let us know in the comments.